Hi, welcome to Sam's Maths Lectures, Sam's Maths Adventures, episode 3. If it looks like a tensor and it quacks like a tensor, then it's a tensor. So, it's been a while since I last made a video, and it's been a while since I last decided I was going to make this video, because somebody asked me, what is a tensor? And obviously I gave the standard physicist response of a tensor is something that transforms like a tensor. And then they asked, how does a tensor transform? And I said, like a tensor. Not very useful. So then I said, a tensor is a element of a tensor product of vector spaces. Again, not very useful. And I'd actually forgotten what a tensor is. So today I'm going to talk about what a tensor really is. So there's three routes that we're going to go down today. We're going to start off with sort of linear algebra and differential geometry, sort of the basic idea of where a tensor comes from, what a tensor actually is, the true definition of a tensor. Then some sort of representation theory, change of basis stuff, which is talking about how tensors transform. And then I'm going to throw in a little bit of category theory and abstract nonsense definitions of what it means to be a tensor or a tensor product anyway. So linear algebra. A tensor is a multilinear map. That is what a tensor is. Multilinear map. So if we have vector spaces v1, v2, up to vn, then basically a tensor, which are all vector spaces over a field K, or they could be modules over a ring R. And tensor is a map T, which goes from V1 cross V2 cross Vn to K, or R, which is linear in each argument. So T of V1, V2, up to, just let's say we've got Vi plus B, Vi prime to Vn is equal to A times with Vi and Vn, and then B times with the primed vector V primed I Vn. Okay, so it's just linear in each of its n arguments. That is what a tensor actually is, sort of the most basic definition. It's an actual concrete definition. It doesn't involve referring to tensors in any way. So a scalar is a tensor because if A is an element of K, then A defines a map from K, which is a vector space, to itself, with X maps to AX, scalar multiplication. It's the most basic tensor. It's sort of a zero tensor because K is not a full vector space when we start talking about tensor products over a single vector space later on. The dual space, V star of V, which is all linear maps from V to K, or R if it's a module. Obviously, elements of the dual space are linear maps with one argument, so that is a multilinear map. So dual vectors are tensors, and because V is isomorphic to its double dual, we can say that every vector is in fact a tensor because it's a map from its dual space to the field, so V star to K, and basically a form theta is going to go to just evaluating it at V, and that is a linear map. Now if we have let's say we've got a linear map F from V to W, this is actually also a tensor because we give it a vector V, it's going to give us a vector in W. So if we give it a vector in V and a dual vector in W star, then theta, underlined the wrong thing there, theta of f of v is an element in K, and this map is linear both in the theta argument and in the v argument, so f is also a tensor. So we could say f goes from v to w, or we could say that f goes from v cross w star into K. Okay, so let's say we have a base v and w have bases ei for I equals 1 up to n for v, and epsilon j for j equals 1 up to m for w. Then what we call the naive tensor product has a basis, so we call it v tensor product w, has a basis ei tensored with epsilon j, and this defines a map from v star times w star to K. So T is in this, then T is going to go from this to K. By if we have A in this bit and we have B in this bit, we say that T, A, B. We'll just pretend that T is one of the basis tensors for now, and then obviously you can build up from later. It's going to be EI, well, A acting on EI times, because these are just in the field now, B acting on epsilon J. And so if we instead have T is, we're going to use Einstein's summation convention everywhere here. So Tij epsilon I tensor EI tensor epsilon J, then it's just going to be Tij A acting on EI times B acting on epsilon J. Okay, so that's how we construct the sort of naive tensor product. One of the most common places where this is going to arise is in differential geometry and general relativity. So we start with a manifold M, and we can consider smooth functions on that manifold, so infinitely differentiable functions into the real numbers. And so we call this C infinity from M into R, and we're actually just going to call this curly C for now. And so if we choose a point P at M, then the tangent space, we call it T at P of M, it is all linear maps from C into R. So C can be viewed as a real vector space, because obviously if you've got two smooth functions, you can add them together, get a new smooth function. You can multiply them by a real number, get a new smooth function. So linear maps from C to R, but it's not just linear maps from C to R, because you also have a product within C, right? You can have a smooth function F, smooth function G, multiply them together, FG, another smooth function. And so we have to account for this extra structure, or we don't have to, but we do, and we say that the map has to be a derivation, or obey the Leibniz rule, which are derivations, and so that means that they obey the product rule. Derivation. So F is a rubbish thing to call this. We're going to call this VP because it's a tangent vector at P, and so VP FG is going to equal F evaluated at P, so that's just a number, times VP acting on G, again just a number because VP is a map into the real numbers, plus G evaluated at P V acting on F. And so what this means is you can actually find that this is a generalization of directional derivatives, where instead of having flat Euclidean space, we've got a manifold. And so this generalizes directional derivative is what the tangent vectors mean. And so each tangent vector is effectively a direction on the surface of the manifold, and we take the derivative with respect to that. And so we can also have a vector field. X belonging to the space of all vector fields, which is this fractor X, we're going to call it. Basically is assignment of VP. So you basically pick a tangent vector at each point, so an element of each tangent space, such that if F is smooth, then VP F is also smooth. So because you get a number at each point by evaluating that tangent vector on the function, you then get a number at each point in the manifold, which is a function. And so if every smooth function you put into your vector field, you get out another smooth function, that is a vector field. It sort of means that your coordinates of your tangent vectors vary smoothly. Now, it doesn't really matter. It's not central to this video. But X is a real vector space, but further it's actually a module over the smooth functions, because you can multiply all your tangent vectors by a smooth function and you'll end up with a smooth function in the end. So a module is just a vector space, but instead of being over a field, it's over a ring, which is a field without necessarily having to be commutative, and inverses don't have to exist. I mean, we're going to assume they are commutative because otherwise it gets horrible. And so then you get associated spaces. You get sort of TP star M, which is just the dual to TP M, and you get sort of tensor products. So TP QR M is TPM, we tensor this with itself Q times, and then we tensor that with the dual space R times, and we get the type QR tensor space at P. And again, you can take, analogously, you can take sort of smooth fields, or it's called a section of the tangent vector space bundle. So XQR. And again, this is a C module, not just a R vector space. And so this is where, if you're a physicist, things will come up, because your velocity of a particle is going to live in a tangent space. Your velocity will live in a tangent space. Your metric tensor is a type 0-2 tensor, because what you do is you plug in a tangent vector and a second tangent vector, and it gives you a real number. This is what G does, and it's symmetric and non-degenerate, and positive definite usually, but not in general relativity because you have negative norms. So G is a bilinear map, so it's a tensor. Is that everything here? Yes. Okay, we have time, 15 minutes. Nice. Okay, so part 2 is going to be representations and basis change. So these two things end up being equivalent. So a representation is when a group acts on a vector space, and basically it means that it gives you, each group element has a invertible matrix that acts on the vector space and transforms all the vectors. It's called an active transformation because you think of the vectors themselves as actually changing. Whereas a change of basis, basically you do the same sort of thing, and the components of the vectors change. So you think the vector is fixed, but the basis is going to stay the same. So let's do an illustration here. So if we have just 2 dimensions, we can have the y-axis, we can have the x-axis, and we're going to have a vector 1, 0. Now what we could do is we could do a representation, an active transformation, and we're going to rotate that vector anti-clockwise by 45 degrees. So the axes are going to stay where they are, but this vector gets rotated up, and so it's now 1 over root 2, 1 over root 2. But we could also define a new basis. So we've got our old basis here, y and x, but then we define a new basis which is rotated 45 degrees clockwise from there. So we've got y prime here, around a bit, and we've got x prime coming down here, and so our vector has stayed where it is, but relative to these this new basis, it has coordinates 1 over root 2, 1 over root 2. And so this is sort of a brief sketch of the fact that active and passive transformations are the same thing, it's just the one has to go the other way around. So we're just going to focus on basis change. So we're going to fix a vector space V, or a module V, which usually in general relativity and whatever, this is your tangent space TPM. And we're going to have a basis EI for I was 1 up to n. And so it's dual space V star. We can choose a dual basis epsilon I for the same I range. And the dual basis is special because epsilon j acting on EI is delta ji, so it's 1 if j and I are equal, and it's 0 if they're not. So any v here can be written as vi ei. So the vi are just numbers, they're the components of v, and they tell us how much of each basis vector to put in. And likewise, any one form theta is theta I, epsilon I, and so the theta I are the components of the form theta. So what are we going to do now? Now we're going to change our basis. So our new basis is going to be in terms of the old basis as e primed I is going to be e prime j times some number aj I, and we're going to sum over all of these. So these just tell us how each basis, what vector each basis is. And you can think of these as the components of e primed I. Now v should stay the same. So v used to be vi ei, and we want that to be the same, so its components are going to have to change in this new basis. So we've changed our basis, and so the components are going to change, but the vector itself will stay the same, right? We've got this blue arrow still goes in the same direction, it is the same size, it's just that the basis has moved. And so what are we going to do? Well, these calculations are going to get tedious, and hopefully I'm not going to write anything in the wrong place, but you will have to bear with me. So this is v primed I, and then we can write this as, actually I'm going to turn these into j's. I have already not been following my notes properly. So this is v primed I, but then this we can re-express as a j I e j. Now we have these on both sides, so we can subtract this side from this side, and we're going to get vj minus v primed I aj ej equals to 0. Now these are this basis, well, it's a basis, so it's linearly independent. So if the sum of all the ei's times some numbers is 0, that means all of those numbers have to be 0. They can't cancel each other out. And so that means that we can just say that vj is aji v primed I. Now what we're going to do is we know that the number of basis vectors has to be the same in both bases, and so that means that A has to be an invertible matrix. Its rank has to equal its n, otherwise you wouldn't get out n linearly independent basis vectors. Okay, so that means that we can find some matrix of numbers bkj such that this thing is delta ki, the identity matrix. And so what we're going to do is we're going to multiply this in here, and we get bkj vj is, well, it's going to be delta ki v primed I, which is v primed k, right? Because when we sum the delta, it's just going to set I to k. And so that is how the components of a vector transform. By v primed I is b ij vj. Just changing k and I around here. That's how a vector transforms. Really, it's how the components of the vector transform, because the vector hasn't transformed. That's the whole point. And so we say that this is contravariant because it's going against the basis, right? The basis transformed with this A matrix, whereas the components have transformed with the inverse matrix B. We're going to do some new notation. We're going to write that Bij for A ji, just to change the indices around, makes it look a bit nicer, which again is B inverse ji. So now let's just recap that the new basis element is Bij times the old matrix elements, basis elements, sorry, and v primed I is Bij times the old one, and just to really make it clear, bjk bji is delta ki. Okay. Now we're going to look at the dual vectors and see how the dual basis transforms. So we've changed to our new basis, so that means that the dual basis needs to be updated, because in general we're not going to have the epsilon j e primed I equals delta ij, so we're going to stick a prime in there as well. We've got a new dual basis. And so this is equal to the old epsilon j on the old ei. I've done these the wrong way around. That's a j, that's an I. Here we go. This is the first of many notational mistakes, I'm sure. So what we're going to do is we're going to expand this out, and we get bik epsilon primed j ek is epsilon j ei. So what we've done is we've expanded this out into the old basis vectors, and then we just pulled the coefficients out because these are linear maps. What are we doing next? Now we're going to hit both sides with a BIL, which is going to turn this thing into a delta KL, which is going to turn this into an L. So epsilon primed JEL, yep, is going to equal BIL epsilon J EI, but then this is still just a delta function. But maybe I never needed this. Maybe I could have just said that from the start. And so I is going to swap with J there. Is that what I'm doing? Yep. Is BJL. And then we're going to re-express that. So BJL is BJK delta KL, which is BJK epsilon K EL. Now that means that epsilon primed J and BJK epsilon K are the same on every basis vector EL, and so that means they're the same on every vector in V, and therefore they have to be the same map, because that's what it means to be the same map. They're equal everywhere. Those are equals. So epsilon primed J equals B JK epsilon K, and so then we hit this with a inverse. No, we don't even need to hit it with an inverse. We're done. Right, so the dual basis now transforms contravariantly. It transforms oppositely to the standard basis. And then similar logic, we're going to find that the components of a one form are going to transform covariantly. What does that mean? It means they transform with the original basis. They transform oppositely to the components of the vectors, because when you put theta on V, you want your outcome to stay the same. And so if the V's are going to change one way, the thetas have to change oppositely to sort of counter that. So this is a covariant transform. Okay, so how does a tensor transform? As I've already said, it doesn't. Physicists like to say a tensor transforms. No, the components of a tensor transform. The tensor itself stays the same, unless we're doing representation theory, in which case it does, but anyway, the point is, let's say that T is a type QR tensor. So we're going to V QR. So again, that's V Q times over with V star R times over. And so writing it out in the standard basis, we have that T is equal to the components now, T I1 dot 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 IQ J1 dot 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 JR times the basis element, which is EI1, tensor up to EIQ tensor epsilon J1 tensor epsilon JR. Okay. Now, I will warn you in advance. When I was writing out my notes for this, lots of the Q's turned into P's. So if I start writing P's and I don't notice, they're meant to be Q's. Okay, but then in a change of basis, we are going to know that this is still T prime, so the new components now. K1 to KQ, L1 up to LR, and then we have new basis vectors. Tensor prime KQ tensor epsilon primed. Oh, I've already made a mistake. These should be upstairs. Contravariant indices go upstairs, covariant indices go downstairs. So then this is L1 tensor dot 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 epsilon prime LR. Okay, I'm happy with that so far. Now what we can do is we can expand out each of these new basis vectors one at a time. So we know that this is equal to B K1, what have I used? I1 epsilon I1. And we know that these ones are B L1 J1 epsilon, the old epsilon J1, and so on. And because it's multilinear, we end up getting a whole new sum, and this whole thing here can then be represented as, so we get T prime K1 da 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 KQ L1 da 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 LR, and now we're going to get BK1 I1 for the first one, and this is going to repeat up to B KQ IQ. And then we get the other way around for these ones, so we get B, L1, J1, all the way up to B, LR, JR. There's a subscript R, you can't really tell, but it is. And then epsilon, I1 tensor, up to IQ. And then the epsilons J1 up to JR. That's just about on the screen. Oh, it's massively on the screen on the video, but my whiteboard is slightly smaller. And then that means that because this is a basis, it's linearly independent, and so if this is equal to this, that means that the two components are equal. So we know that T I1 up to IQ J1 JQ is equal to, let's just copy and paste this whole thing. It's still quicker than writing it. And let's rewrite in the T. Okay, so we've got this. Unfortunately, this is the wrong way around because it's taking us from the primed to the unprimed, but we want to start with the unprimed because that's what we originally had, and then we updated our basis and we're updating. So we just go through and we update. So if we stick in a factor B, AS, and IS in front of both sides and sum it up, then on this side it's just going to be a B, A1, I1, let's say, in front of this. On this side it's going to hit the relevant B here, and so it's going to combine with B, KS, IS to give delta AS, KS, and so it's going to swap this, the KS up here, with an AS. Likewise, when we stick in a B, BS, JS, then it's going to react with a B, LS, JS to give a delta LS, BS, which is going to swap one of these B's into one of these L's into a B. And so what we end up with is the components of a tensor transform as T primed A1 up to AQ, B1 BR equals to B A1 I1 up to B AQ IQ B B1 J1 B BR JR times T I1 IQ B1 BR. That is how the components of a tensor transform. Obviously I've done it so that all my V's were first and all my V stars were second. I could have had something mixed like T A B C, and then the prime of this is just going to be B AI B B J B C K T I J K, something like that. You just read all of the factors, it doesn't matter. Okay, so the last bit now, category theory or abstract nonsense. I'm not going to get into the depths of this. I'm not going to talk about adjunctions and what a natural isomorphism is and whatever, because that's for another video. But if V, W, and U are k-vector spaces, then the tensor product V tensor W is an object, or it's a k-vector space with a bilinear map from v times w into v tensor w. So in our standard tensor product, vw is going to go to v tensor w. It's pretty boring. Such that this is what's called a universal property for all bilinear maps f from v times w into u. So any vector space map from v times w into u, which is linear in both arguments, there exists a unique map f star from we're going to call this I, by the way, like the insertion, inclusion. It's not necessarily injective because it's not. 3v and w will go to the same as thing as v and 3w because it both goes to 3vw. So it's not injective, but it's an inclusion. I'm going to call it I anyway. I don't care. So there exists a unique f star, which is linear from v tensor w into u, such that the following commutes. So we have v cross w, we have our bilinear map I into v tensor w. Oh, what have I done? Stop it. Okay, we have our map into v tensor w. This is actually part of the tensor product. So whenever we have a sort of universal object in category theory, it actually comes with some arrows usually. So when we have the product of two vector spaces, it's not just the vector space which is the product, it also comes with projection maps onto the original vector spaces. So I is also part of this package deal. So that whenever we have f, which is bilinear, into u, then there exists a unique f star such that this whole thing commutes. And so that means that f star of I of v w is always going to equal f of v w for all v and all w. So now let's prove that the tensor product we talked about earlier is the tensor product. So let's have EI and epsilon on j be bases of v and w. Then we can define f star by its point on the basis. So first of all, f is defined by its values f on EI epsilon j. If you know all of those, then you can expand it to all of v times w. F is fully defined. That's a good way to completely and uniquely define f, is its values just on those basis vectors. And likewise, f star is defined entirely by its value on the basis epsilon I tensor epsilon j. Then what we can do is we can say that I of v w is just going to be v tensor w, so that's going to be vi wj ei tensor epsilon j as our map there. And so if we set this, we're going to define this as equal to f of ei epsilon j, then that completely defines everything, and we find that f star of I of v w is f star of this thing. So these just fall out because it's a linear map, and then we evaluate it on these basis vectors, which is f ei epsilon j. But then this map is bilinear, so we can pull the v into this argument, we can pull the w into this argument. Obviously we could do it the other way around, but that wouldn't make sense. That is f vi ei wj epsilon j, which is f v w. So our tensor product is this abstract nonce tensor product as well. Brilliant. Now, the tensor product is unique up to unique isomorphism. Now, what does that mean? Okay, let's say that we've got I into x and j into y are valid tensor products. As we had before. Now, that means that, first of all, we have v cross w, I into x. Well, x is also a vector space, so we can put x down here, and then I is a bilinear map, so we can put I down there, and then because x is the tensor product, that means that there's a unique map which makes this commute. Now, the identity on x is a map that makes this commute, and that means it has to be the only map. There's no other automorphism of x which is going to preserve that I. And similarly for y. So the only arrow you can draw from x to x that makes that whole triangle work is the identity. Now, what we can do is we can have v cross w. We're going to have an I coming out here to an x. We're going to have a j into a y here. We're going to have an I down here into an x. And we're going to have another j into another y here. Now, because of the unique property, j is bilinear, x is a tensor product, there is a unique j star that makes this work. And obviously that must also be j star because we've got the same diagram. And again, y is a tensor product, I is a bilinear map, so there is a unique I star. But we can compose these arrows, right? And if this triangle commutes and this triangle commutes, then we can compose that arrow and the result is going to commute as well. So we have here I star composed with j star, and we have here j star composed with I star, but we know that the only arrow from x to x that makes all this work is the identity, and we know the only arrow from y to y that makes this work is the identity, and so we get that I star composed with j star has to be the identity on x, and j star of I star has to be the identity on y, and so that means that I star is the inverse of j star, which means that we've got an isomorphism x to y. But more importantly, there's a unique isomorphism, right? Because we were forced to choose that I star, that j star. There was no second thing. So we have this unique isomorphism, and that's what's great about these sort of universal properties, is we get some object which isn't really unique because there's different ways of writing it, right? We could have v tensor w, but we could also have w tensor v, right, where we just put the basis the other way around. That is also a tensor product. That's perfectly fine, but those are isomorphic to each other. Every tensor product is isomorphic to every other tensor product, and there's a unique way to go between them. So it's not even like we can get confused. Like, we can always replace it in a diagram in the same way because that isomorphism is unique. That's what's really important. And so the isomorphism, of course, takes VW to WV, and vice versa. Okay. Lots of other sort of categories admit a bilinear product. So abelian groups. So if A and B are abelian groups, so that means they've got a commutative associative product with identity and inverse, then A tensor B is all, I think, finite sums 1 to n, AI tensored with BI, but they have the important property that we then modulo out some relation R, which tells us that A1 tensor B plus A2 tensor B is A1 plus A2 tensor B, and A tensor B1 plus A tensor B2 has to be A tensor B1 plus B2. Right, so we just keep that bilinearity. And then these tensor products are sort of used because they have the useful property that they're commutative and they're associative. I haven't shown that, I'm not going to show that, but based on the sort of naive construction, it's very clear that V tensor W tensor U, you don't have to put brackets in there, right? You don't have to say V tensor W tensor U, because this is just isomorphic to V tensored W tensored U. So this is the basic point for a monoidal category. We've also got that K tensor V is isomorphic to V for any vector space V over a field K. How do we know that? Well, K doesn't have a basis. It's got like an empty basis. Or maybe we could show that using the unique property. So what we've got is we've got K times V here, which is all pairs A, V. Then we've got to map F into another space W. We're going to say that this is just going to basically map that to A times V in V. Is there a unique map here? Well, this is bilinear, and so that means that A plus B, F of A plus B, what am I doing? V is equal to FAV plus FBV and FABV equals AF BV, but we can actually go one further. We can say that F of AV is equal to AF1V, which is F1AV, and so this is also a vector, V primed. And so this map is entirely determined by what it does to 1V. 1V goes to V, and so this map is just F on 1 times V. Does that work? Yeah. And so that is the unique map, and so we see that K tensor V is just V. So we have this unit, we have associativity, we have commutativity, usually. Sometimes you can have a braiding and stuff where it doesn't quite work. But yeah, so tensors give you monoidal categories. Lots of things are monoidal categories. I think maybe my next video will be about topological quantum field theories, which use a certain type of monoidal category, which is really cool because it doesn't actually have arrows. It has cobordisms. Okay. Thank you for watching, and I will see you next time.